Actually kind of doing is, we're actually, if you've got the book, go to page 9. We're starting with chapter 1. And we're dealing with processes. And we're also going to be dealing with acronyms, the terminology. You're going to hear a lot of terminology. You might not know it all right now. That's fine. You're actually going to be doing list of terms for you to start learning. This isn't homework or anything, and you may actually know quite a few of these. But if you find one that you don't know, it's going to be something you're probably going to want to look up. Maybe write the definition down, and just kind of start getting used to these terms because they're used quite often. So, on that page 9 there, you see that chart? Yeah. Okay. How many welding processes does it show on that chart? Drop the comment, just take a guess. Over 100? Very possibly? Yeah. Lots. Let's put it that way. So, what ends up happening is this. There are lots of welding processes out there. There's a lot of cutting processes out there, but not everything is easily set up to teach. It could be because the machinery is very expensive, or the machinery is really big, and we might be limited on space. But we can actually break down quite a bit of it down to these 5 processes right here, especially because we're going to focus more on manual welding versus operator ideas. Operations, when you're just running a machine and the machine does most of the work, very valid in terms of welding processes, but for us to learn it, it's not really a viable system to bring in just to learn how to run the machine. You really need to know what's going on during the operation. And we can kind of tie most of that kind of stuff into these processes. So even though we've got 100 different processes on that chart, we're going to be really focusing on 5 in this program. A little bit more than that, we can break out, say, plasma cutting into CNC plasma cutting or manual plasma cutting. We can break out MIG welding into flux core welding, into robotic MIG welding, and so we can break those out a little bit, but these are really the gist of what we do in this program. So these are acronyms. So we're going to start with the very first one. And that's oxy-fuel cutting. Now, if you notice there, I did not say welding, I said cutting. We actually have eliminated the oxy-fuel welding out of the program because essentially it's a really old school process that the skill set itself is really already taught in the GTAW process. This is what I'm on here. So, in terms of, say how viable it is for jobs, it really isn't anymore. Occasionally you might come across something where it needs to be oxy-fuel welded, and it's not even done all that much anymore. Steel mills used to do it more often with cable changes on overhead cranes. Even now, although if we take the 2 that are around, U.S. Steel still does oxy-fuel welding on their cable changes, but AK Steel, they've actually switched their system to where it's being arc welded. So, even then we're kind of losing some of how much oxy-fuel welding we have. So we're going to focus on oxy-fuel cutting. And this has been, besides forge welding, this is really one of the older styles of whatever, whether it's processing for cutting or welding. This is really one of the oldest ones that were out there. So this process does a couple things. One is that we introduce oxygen into the mix of things. Is oxygen a flammable gas? Have you ever looked at an oxygen tank? It says nothing about it being flammable. It's not flammable. It's an accelerant. So you won't see anything that says flammable on the thing. It's an accelerant. So what it's doing is we're taking already an open flame and making it hotter by adding oxygen to it. But it also does another thing. It creates an oxidizing process, which is actually the cut process. So we're going to then introduce a gas, a fuel. There's lots of different types out there. We use propane, or a derivative of propane. It's called chemically. And propane comes from where? Where does propane come? Yeah? No? The distillation of crude oil. One of the gases that is made through that process is propane. So it's not just making gasoline, you're actually making lots of different things out of that oil, of that crude oil. What is another gas that's used? You guys heard of acetylene? Okay. Where's acetylene come from? That one I don't expect you to know. I'm going to be throwing a lot of questions. You're going to go, I don't even know. And that's why we run this course like this, okay? Because there is a lot of background information that a lot of people just don't realize is, what's going on. So acetylene, actually, have you ever played with dry ice? Really? You never made dry ice bombs? No. Come on. A little dry ice and water into a pop bottle and throw it. Okay. When you put dry ice into water, it starts releasing a gas, and that's carbon dioxide. Basically, you can carbonize, like, if you got, say, let's just, for example, you got syrup, that's a root beer syrup, and you add the water to it, and then you throw a chunk of dry ice in it, you would carbonize that. So you make it fizzy. This releases CO2. So it releases this CO2, it releases bubbles. You also get that fog effect too, and that's really what's going on too. If you replace the dry ice though, and the water with water and a rock called calcium carbide, it does kind of the same thing. It starts releasing a gas. Except for in this case, it's acetylene gas. So you actually just add water to calcium carbide and you get acetylene. It's pretty simple. Nothing, you don't have to look up on the internet or anything. It's just in your textbook. It's not like we're going to make bombs out of it. But you could, I guess. So acetylene is a pretty volatile gas. It's been used forever and ever and ever. But it's a pretty volatile gas, and it's very expensive. And there's all kinds of little issues with acetylene, but it still works really well. Our main thing is that it's not very cheap. So we've switched it over because propane actually works just fine for cutting, where acetylene will really shine for the welding side of things. So we are using this propane gas. There's other gases. There's nat gas. You can use natural gas. You can use a hydrogen gas. You can use all kinds of stuff that will light up. So, did you have a question? So the way it cuts though, so here's the thing. You got torch, and the torch has adjustments for the gas and the oxygen, but it also has a lever. And the lever is for a high pressure string of oxygen that comes out the center of the torch tip. What's another form of oxidation? Y'all experience it. I'm sure you do. You ever heard of rust? Okay. That's oxidation. That's iron oxide. So bonding of oxygen molecules to whatever the material is. Aluminum, iron oxide makes rust. Aluminum makes just this coating that's kind of shiny. So what we're doing is we're actually oxidizing, we're not cutting through heat. So what the torch is really there for is to heat the piece up. And we're getting it just underneath the melting temperature. So if we melted it, it would just melt. It wouldn't actually have a cut line. Okay? So what is the melting temperature of steel? Take a guess. Throw something out there. 2,500. Close. Very close. 26 to 28, depending on the carbon content. So we need to get it up to about there. Right in there. And then what ends up happening is steel kind of expands a little bit. That's what happens when steel gets hot. It opens up the molecules a little bit. The oxygen molecules are really small. When you hit the lever from the high pressure string, it literally goes into the molecules. It kind of gets in there. And basically it supercharges the oxidizing system. The process. If you took your hand and rubbed it across a piece of rusty steel, would you come away with stuff on your hand? Yeah, absolutely. Kind of the same thing happens here, except for it immediately, instead of over time, it immediately makes that stuff just all turn to powder. And when it turns to powder, the stream, the high pressure stream, then blows it away. And then that area then becomes, you can start moving it, and you keep going, and you get a cut line. That's called a curve. That line, that cut area is called a curve. That's going to come up sometime. Okay? It's also on your list. So we don't actually cut with melting it, we cut with an oxidizing process. You get really good, with the torch, then you can expand, you get better and better. Graduate to something like this. This is a torch. This is not a precision cutting tool at this point. So what I was actually going to show you though, these are your two valves, and then this here is the oxygen valve for the high pressure screw. So you would have this on, you would have a flame coming out, that's your preheat, you push the lever down and cut, that gives you a high pressure screw going through. You got three tubes here.
About people chasing around.
Yes. Well, you don't do that. You're kind of just pushing it in. It'll open up a little hole.
Okay.
So you want to have a little bit of a gap.
And that's from the back side?
No, front side. Okay. You're always welding from the front side. Think of this being like the inside of the pipe. You can't weld the inside of the pipe.
Okay.
So that would be, that's how we weld it. We want the weld to go all the way through.
Oh, okay.
So on the other side of it, we have this one. Plasma arc cutting. Plasma arc cutting. It's an electrical process. So, any idea what plasma is? Okay. You better science teachers. So plasma is the fourth form of matter. We've got solids, liquids, gases, and then we have plasma. Plasma is essentially a gas, but it is a gas that we've ionized or electrified. Gases in general, you don't think about gases actually being able to conduct electricity. But in this process it does. But because it's so different, because it is ionized, it's a different form of matter. So what we're doing is we're going to introduce an electrical arc into a gas. And in our case, all we're using is shotgun. Nothing special, just compressor. We throw electricity into that gas together and we ionize it. and it really kind of supercharges the gas. And then we take that gas and the arc and we make it go through a little tiny orifice. Same kind of principle as taking, say, a water line, say yay thick, and then putting a little tube on the end, yay thick. You're going to get pressure as it goes through that smaller hole. You get flow here, and then it'll build pressure trying to get through that smaller hole, and it'll spray out from it. Kind of the same thing happens. Only what we're going to do is we're going to get a really supercharged, hot arc coming out of the torch of the plasma cutter. So what we get is we get an arc that comes out at about 20,000 degrees. So we already know what the melting temperature of steel is. We're way, way above this. So in this case, this is a melting process, but it melts at such a high rate at 20,000 degrees that you get a nice clean cut. And it's not going to spread the heat all that much. It's going to be super concentrated in one little area. So our curves are actually going to be nice and tight. There's limitations on both systems, okay? In terms of the torch cutting, lots of heat. The heat gets dissipated all over the place, but you cut really thick materials. I've cut, with a hand torch, I've cut up to 16-inch thick slabs. So you can cut thick pieces with it. You just got to have the right tips, right pressures, things like that with the tanks. But it throws a lot of heat everywhere, so the thin material is not that great on thin material. It will warp it all over the place. You know, you get funky cuts. So there is limitations there. So plasma cutting is just kind of the opposite. It's really good on thinner materials, but on thicker materials, it doesn't do really well. Most systems, if you were to get 1/2 to 3/4 inch thick cuts out of it, you'd be doing really well. That's about as much as you're going to get. It's pretty limited that way.
You're saying the plasma can't go past 3/4, or it can, but
It can, and you got to really get a pretty beefy system. Most of your just normal systems that you buy, that's about as thick.
So is it the heat factor that allows you to get so detailed with the plasma cutting?
The heat and the focus of the arc.
So the tipping is also as well.
Yep. Like our system back there, our hand system is a military spec ESOP that, if you look at their specs, it says that you can go up to 7/8 thick. I've done 1/2 inch. I might be able to pull off 3/4, but I'm not sure.
Yeah.
You know, our system on the CNC plasma table, it says I can go up to 1.5 inches. That one's a pretty beefy system. I would say probably the max is going to be maybe 1 inch, maybe a little bit more than 1 inch.
Yeah.
But that's really thick for a plasma. So those are kind of the limitations on those, you know, good and bad. You get really nice clean cuts out of the plasma cutter. You can do some pretty close to precision cutting.
Yeah.
So those two systems are actually what you're going to be introduced to in 102. You're going to be using both of those systems. And you're also going to be using the rest of the shop tools and stuff like that, because you're going to be doing fabrication. Then we go into welding. So we've got 3 main welding processes. So for the longest time, people just assumed that this was called arc welding. Shielded metal arc welding. A lot of people say, you know, what kind of welding can you do? I arc weld. Well, that's kind of hard to differentiate, because guess what? This is also called arc welding. This is also called arc welding. So they all are called arc welding. So it's really not a distinction. Then some people will say it's stick welding. Okay, yeah, that's kind of a more appropriate name, but it's more of a slang term. It's not a real correct term. So shielded metal arc welding is the correct term for this. Or if you're in Europe, they may call it MMA, which is manual metal arc, or metal manual arc, something like that. But here in the U.S., we use shielded metal arc welding. So this was one of the earliest arc welding processes out there, besides some a little bit of spot fusion. So this is an arc welding rod. This is an electrode. It's also our filament metal. So this would be what you would use to do some welding with. Back in the day, back in the late 1800s or so, basically they had no coating on it. It was just bare metal. Didn't get very good welds. They would actually connect this up to batteries, use the amperage off the batteries to do the welding. It wasn't even running off of a generator or something like that. So not that good back then. They were still kind of perfecting the process. It wasn't until someone got the bright idea to put this coating on. And really what the idea here was that they needed to protect the weld from the atmosphere. The atmosphere is the enemy of a weld. Whether it is hydrogen getting into it causing hydrogen embrittlement, whether it is oxygen getting into it causing porosity, there's lots of little impurities that get into it from the atmosphere. So we want to protect it from the atmosphere. So the shielding, that's the name, when this starts burning, it creates this little pocket of gas over our weld and protects it from the atmosphere. It just kind of sits over the weld. This is kind of the game changer. This is what made this process much, much better. There's a couple things this also does. If there's any kind of additives like alloys, it's going to be in powder form here. It's not going to be in the metal part because we basically got a steelmaking furnace sitting in front of us as everything melts together. So it just kind of melts out of the flux. It also will produce a slag. Slag is made there for a couple of reasons. One is to kind of protect it. As we move away, that gas follows us. It's a protective coating to keep the atmosphere out until it's solid. It also helps hold the heat in, actually, so it slows the cooling process down a little bit. By doing that, you're going to maximize the ductility of the weld so it doesn't crack. So that's where the shielded metal comes from. This process, has been around for a while, but yet it's still very viable today. It's still one of the best processes for using outside, underwater, in bad conditions, in places where it's hard to get a machine sitting there near you, but you can run a long cable. So this is really still a pretty big process in the industry. Probably 65–70%, I would say, is still stick welding. So this is still, even though it's pretty old school, it still gets done a lot. So it's good to know this one. The way it works is pretty simple. So, did you take any electrical classes when you were over there?
Minor.
Okay. Did you ever learn about Ohm's law?
To be honest, we did, but I can't remember.
It's okay. We're not doing the math side of it at all. This is more of a conceptual thing.
That was mainly what it was math portions.
Right. Yeah, that's what's always kind of funny about electricity is that there's so much hands-on to electricity, yet they start you with math. So it's kind of like, okay. So conceptually, what we're doing is basically we're creating a circuit. And in a circuit, per Ohm's law, we have amperage, we have voltage, and we have resistance. Amperage and current are the same terms, so it's moving like that. So that is important in the way it welds. So let me kind of give you a little example. Okay, what do we have? Light bulb. Now, what kind of electrical circuits are out there?
Series and parallel.
Okay. I'm sorry. How about power sources?
Oh.
AC and DC. There you go. So AC is what? Alternating current. Why is it called alternating current? What happens? What makes it alternating current?
Goes up and down.
Goes up and down. What's actually happening? Any idea? is actually flipping from positive to negative. So really what's going on is the polarity is constantly changing. Polarity is the direction of the flow. So it's constantly changing back and forth. The other one is direct current. Direct current doesn't have that change of flow. It stays in one direction, or we switch out the system and then it goes in the opposite direction, but it's still a direct current. It doesn't change. Okay? So we're going to call this an Edison light bulb, because Edison was a proponent for DC. We like DC. We like welding in DC. AC, not my favorite. Not my favorite to weld with. Reason being is that that change of direction, if you look at an oscilloscope will show you on the screen basically the movement of the electrical current. It goes positive, negative, positive, negative, positive, negative. And there's a line in between. Any idea what that line is? What's that? What's that? What? Okay. Can you put a pass over that?
Yeah.
Okay. So that little line in between, though, is a 0 point. Technically, 60 times a second, there's no electricity because it has to cross over, and it hits that neutral point. So welding, not such a great thing. Direct current stays in one area, doesn't lose. So we like that. So we're going to say this way. We're going to have electrical flow that comes up this guy, goes across this filament, and goes back down. Now this is a atmospheric thing. We basically reduced any kind of atmosphere inside this. That helps to keep this from not breaking, but we understand that it does break. What's the filament made of? You heard of tungsten? That's what the filament is made of. Any idea why?